The change in enthalpy, delta H, is for a particular reaction. If you have a different reaction, then delta H changes. So if your chemical equation is multiplied by a factor, say if you double the number of moles, then the heat change is also going to be doubled, right? If you burn twice as much gasoline, you'll get twice as much energy. So if we had a reaction A plus 2B makes C, and that had a value of delta H1, here we're multiplying all the coefficients by 2. We're doubling the amounts, so then delta H is also doubled. So that works if you're dividing by something or multiplying by something. If a chemical reaction, a chemical equation is reversed, then delta H changes sign, right? So if I am, well, it's hard to unburn stuff. Well, let's just think about an ice cube melting. So when an ice cube melts, it's absorbing energy, right? It's an endothermic process. When an ice cube freezes, it gives off heat. Now, it's not doing that spontaneously. You're putting it into a freezer with an engine and a compressor and stuff that is pulling the energy out of it and making it colder. But if you go one way, it's positive. If you go the other way, it's negative. Does that make sense? So here, just reversing the reaction, you change the sign. And then there's Hess's law. So if we can express the chemical equation as the sum of a series of steps, then delta H for the overall reaction is the same as the sum of the heats of reaction for each step. So we're looking here at A plus 2B making 2D. But if we know that A plus 2B making C has this delta H, it's absorbing energy, and then when C reacts to form 2Ds, it's releasing this much energy. This one is equal to the sum of those. So this distance is equal to the sum of those. This is positive and this one's negative. So this makes it possible to determine delta H for a reaction. It's not, all of these delta H things are not super precise. But we can do it without actually measuring it in the lab. There are some reactions that would be very hard to measure delta H for. So you can manipulate reactions that have known delta H's to get the reactants of interest on the left, the products of interest on the right, get everything else to cancel out, and make appropriate changes to the delta H's, and then you add them together and you get the delta H for this reaction that you didn't know before. So let's look at this one. Here we have 2A plus B makes C, and the heat of reaction for this is 122 joules. They're asking us, what if I had 2C going to 4A plus 2B? All the coefficients have been multiplied by 2, right? So I'm going to take that 122 and multiply by 2. What else has happened? We're going to change the sign because this is going backwards compared to this one. If this one's positive, then the other one's negative. So it must be this one. Does that make sense? Okay, let's look at this one. A little more complicated actual chemicals. So we're supposed to find the heat of reaction for this equation, And we are given these other reactions and their delta H's. The nice thing about these problems is they don't give you stuff you don't need to use. Right? If you're actually trying to do this, you've got the CRC and there's about this many pages of reactions with delta H's, and you have to go through there and find ones that you can put together, and it takes a lot longer. So we're just going to deal with these three. So this is what I like to do. I'm going to highlight these with colors so that we can see what's going on here. So I need to figure out how to take these equations and add them up so that I get this. So first of all, I'm going to find an equation that has this guy, N2O, in the gas state as a reactant. So I'm looking for N2O as in the gas state. Well, that's this one right here. Yeah? I don't see it anywhere else. So I'm going to write that one down. So 2 N2O in the gas state goes to 2 N2 gas plus O2 gas. And so delta H is negative 163.2 kilojoules. So there's the red one as a reactant. Is this the right coefficient? This 2. Up here I only have 1, right? How can I get this to be 1? Divide by 2, right? So I'll divide this by 2, and so that becomes a 1, and this becomes a 1. And what happens when I divide 1 by 2? You get 1/2. Which, if you're talking about molecules, doesn't make sense. But if you're talking about moles of molecules, you can have 1/2 mole. And so then I also need to divide this by 2. Divide by 2 or multiply by 1/2, whatever, however you want to think about it. So negative 163.2 divided by 2. That's negative 81.6 kilojoules. So NO2 is another reactant, so let's locate that. There's NO2. So it's the product there, so I need to write the reaction backwards, right? So I'm going to write that one backwards. 2 NO2 gas. It's going to make 2 NO plus O2. Delta H is negative 113.1 kilojoules. Because I reversed it, what do I do to delta H? Change the sign. It was negative, now it's positive. Going the opposite way. So this is my NO2. Does it have the right coefficient? No, it doesn't. So we need to divide this equation by 2 also. And we're going to get another 1/2 there. I'm going to take this guy and divide by 2. 113.1 divided by 2. So this is 56.55 kilojoules. I'm going to put a plus there just to tell myself I thought about it. This is what it's supposed to be. Okay, so now let's look for this guy. Well, he's here and there. So this guy's right here. So I've got the 2 reactants I want. I have the product, but I also have nitrogen and oxygen. And they can't be in here. So if I take this reaction and stick it in here, what am I going to end up with? N2 gas plus O2 gas goes to 2NO gas. And that's my NO that I'm looking for. Delta H for that one is plus 182.6 kilojoules. Haven't done anything to it yet. So I want nitrogen to go away. So this is making a mole of nitrogen, and that's using up a mole of nitrogen. So we could think of those as canceling out, right? That one cancels with that one. Over on this side, I have a half and a half, a total of 1 mole of oxygen that's being produced, and this is using up a mole of oxygen. So those guys go away. And now what I'm left with is N2O gas plus NO2 gas makes one of these plus 2 of those, that's 3. I didn't do anything to this guy. I'm just going to write his, let's do this. (186), 182.6 kilojoules. So I'm going to add those things together. Negative 81.5, 56.55, and 182.6. 157.65, 157.7 kilojoules. So delta H for this is 157.7 kilojoules. Any questions? There will be a problem like that on the 3rd exam, but not tonight. I think our brains are full.